So I managed to make it to this slide yesterday on monotonic reads, and I hope that the idea was clear to everyone. Basically, I'm now looking at a single process moving from one location to the other. The model is that that process logs into a fully distributed database. That's the best way of thinking of it. And the fully distributed database means that you log into, let's say you were over here, you move over to that side, and then you log into this thing. And then the basic idea of client-centric consistency is that whatever you did and saw over here will be available to you over here. And the big difference with data-centric consistency is that if you propagate an update, then in principle, that update should be propagated to all the replicated stores out there in your system. Not so with client-centric consistency. Okay, so, I explained the notation. I'll skip that one. And the example that you can typically think in terms of a monotonic reads is that if you're, I don't know what this is. If you're looking at your personal calendar, then you basically just see increments on that calendar, okay? And the same thing is that you may actually even experience this, like I explained yesterday, with synchronizing your cell phone with your desktop or whatever mail system you use. If you look into the mail system or your email system, which you also have on your cell phone, if you don't modify anything, what you should be seeing is that your mailbox just is growing and growing and growing. Yes, I'm also used to that, although I'm very good at removing mail as well. Okay, hold it. If you take a look at systems like Google Doc, or if you would even take a look at the calendar example that I just mentioned, what you would normally see is that there is a centralized database for that calendar, and that you explicitly synchronize your local calendar with the one that is stored on your smartphone. So if I take the calendar example, then if you're over here, your full calendar is available to you here. Okay, everything's there. You do your updates, you read your stuff, that's it. And I'm not giving you full information at the moment. Then when you move to that side over there, you will not have an up-to-date calendar. Now, client-centric consistency, certainly with monotonic reads, guarantees that when you log into the system again, that this database will have the same information that you had over here. So hold it. Now, and this is also very important. You have to make a very clear distinction between the specification and the implementation. The specification of a client-centric consistency in the case of monotonic reads says that whatever you read over here will be available over there. Okay, so once you log into the system again, monotonic read consistency guarantees that you will see exactly the same information and perhaps some updates. How could you implement that specification? Well, at the moment that you log in, you provide, for example, information on where you came from. And at that moment, this database under the hood will fetch your calendar from that database, place it there, and only then will it make your calendar visible. That's an implementation issue. Got it? There's another implementation that you could do, that the moment that you log out over here, you broadcast your calendar to all these databases, including this one, and you don't know where you're going to log in again. Then at the moment that you log in by coincidence to this database, you will actually see that calendar as well. That's also an implementation that meets that specification. Make the distinction between the two. Okay? Does that clarify things? Yes. Okay. So here's one with monotonic writes. Very much the same thing. Again, let me just emphasize the notation again. This is a write operation that led to version 1 of X. Okay? and I did this at location 1. Then, when I move over to location 2, and I want to do another write operation, then monotonic writes guarantees that all the write operations that led to version 1 of X will have been performed at location 2 before I do this write operation that leads to version number 2 of X. So basically, I am updating stuff that I had updated before. Okay? And perhaps a bit more. But at least the updates are performed on something that I had seen before. So this one is not adhering to monotonic writes, because I am not given any guarantees that the version of X that I'm producing over here is based on a version of X that I was working on before. Does everybody see that? So the second example does not give me these guarantees. Typical example, I guess I like the second one the most, maintaining versions of replicated files. So that means that as soon as you want to update files, you move to another location, your updates move along with you. That's an informal way of thinking of it. You will always be, regardless whether you are actually reading things, as soon as you start working on updates, what you were working on will be available to you on this new location as well. That's the model that you should keep in mind. Okay? I like this question. Does a monotonic write consistency imply monotonic read consistency? What you're doing is making a very clear distinction between reads and writes, and monotonic writes only says something about the writes. So regardless how many reads have taken place at location 2, even yours perhaps, if monotonic reads are not guaranteed, then every time you do a read at location 2, could be on any version. But as soon as you start to do a write, it will make sure that you actually write on the operation you had, on the data you accessed before. Yes. The common mistake that people tend to make is that when you write, you automatically read. That's not the case. Okay? You would be correct, so to use that word, if a write implied that you would also do a read. But that's not the case. You just blindly append data to a file. And now you want to make sure that the file that you're appending to at least contains the data to which you previously appended data to, without even reading the content of that file. Okay? And read your writes is exactly this. I did an update at location 1, I moved to location 2, and hopefully when I read something, I read the stuff that I wrote over there. And my canonical example here, which we all know, and which also illustrates that the notion of a location can be something abstract, is when you are updating your web page in a completely separated system from your web browser. Okay, so you could use an ordinary HTML editor or a text editor or VI, whatever, to update your HTML pages. And then when you go to your browser and you do a simple click, you may not see the update. You are not reading your writes. And what is happening is that the cache gets in the way. And what you need to do is you need to do a shift reload, and that will bypass the cache and get the data from the actual web server where you did the update. So the second case is a read your writes, and the first case is just read the cache again, but that's not implementing a read your writes semantics consistency. Is that clear to everyone? And again, watch the notation. I do a write at location 1 through my text editor, and that leads to version 1 of my web page. And then I move to the other location, my browser, and I if I may read a new version of X because maybe there are concurrent updates on this file. And what this notation says, that the version that I'm reading is based on a version of X that I've previously had, namely the one that contains all the write operations that led to version 1 of X, including perhaps write operations that led to version 2 of X. And then I'm a happy camper. Okay? And in this case, I don't have this. I was writing to X leading to a version 1. I move to my browser to discover a version 2, but that version 2 is not guaranteed to contain all the write operations that I just performed in my text editor. That's what this notation says. Okay? And then finally, you have writes follows reads. A write operation by a process on the data item X following a previous read operation on X by the same process is guaranteed to take place on what you just read. Okay? Or a more recent version. So here again, you have the write set that led to version 1 of X. You read this version 1 of X. You move to another location. You want to update X, leading to perhaps a version 2. I should say, I think this should be a 3 actually. Doesn't matter. A new version of X. And what you will be writing is based on something that you read before. So that means that the write operations that led to version 1 of X will be available over there. Perhaps a number of additional writes that led to a version 2 of X. And that's the reason why this notation is not entirely correct. You do a write operation that will then lead to a version 3. No. Okay. So the question was essentially, what is the relationship between this write operation and this write set? Now, what this notation says is what I will be writing on. Okay, and now I see your point. What I will be writing on or updating is at least the version of X that I read before. And that is contained in this part of the notation. The write set that led to the version 1 of X, yes, is available at L2 and has been executed, along with perhaps additional write operations that led to a version 2 of X, so that means a fresher version of X. And then when you do a write operation, you will be leading to an X3, but it is at least based on something that you had read before, and perhaps some updates. No, L1 is not a process. There's only one process moving from location 1 to location 2. And at location 1, it read version 1. It moved to location 2 to find a version of X. And that version of X is guaranteed to contain to be at least X1, but perhaps has been updated after you have read it. That's all fine. You will then update that version of X, which is based on what you previously read, and then bring it to a version 3. Does that answer your question?
Yeah, but I don't see why you would not read before you actually write.
Why you would not read before you would write?
Why is there no read on location 2 before the data is written?
Oh, it's just not there. Because, it doesn't have to be, no. Think of this as, yes, let's take appending information to a file. So what this statement then is let me see what's in the file. Okay? And then what you do is you move to location 2 and say, okay, let me append some data to that file.
So it's not changing, it's really appending in this.
And in this case, it would be appending. So, but this is a write operation on the file, right? Mm-hmm. Okay. Now, what this picture doesn't show in this example is that there may be multiple processes working on that file, notably at location 2. And they have been appending stuff to that file as well, but they will be appending stuff to the file, to a version of the file you saw before. Maybe a replicated version, that's all fine, but they are appending to the file that you had seen. and on which you based your decision to append some data as well. And now you will be appending more stuff after the other process that had appended other material. Does that make sense?
Yes.
Okay.
Version 2 is lost. For X3, X2 is lost.
Yeah, in my notation, what I should say is that this thing leads to a version 3. And otherwise, that's the reason why, otherwise I will be overwriting X2, and that's not what I was intending to do. Okay? And for the same reason, this one is not abiding by writes follows reads, because you're reading a version of the file at location 1, and then there was another version of this file, version 2. Could be completely different append operations, and when you move to location 2, you'll be operating on that copy of the file. No guarantees are given that is based on what you had read before. Yes?
So the dotted line, the curvy one?
This one?
No, the curvy one.
This one?
States that it's the intention to update provision number 1.
No, what this thing actually, what I tried to make clear with this thing is that you move from location 1 to location 2.
Why would the latter one be wrong? There could be some other processes that created version 2.
True, but in this notation, I have no guarantees that I'm also operating on the version that I read before. Because in that case, I shouldn't use this notation. I should have used this notation. Okay? More important to me is, the notation is explained again in the book. More important to me is that you understand the semantics of this consistency model.
What if we have another?
Oh, hold it. What I told you yesterday, and maybe this is the confusing thing, the version numbers do not indicate that version number 2 is the successor to version number 1. Okay, so that's very important. So version 2 could be concurrent to version 1. Okay, so far so good. So there was a process operating on location 2, and let's just make this very concrete. I start with an empty file, okay? And then at location 1, there was a process that appended the value 10 to the file, okay? And that's my version 1 of that file. So when I read that file, say, oh, 10. Okay. There's another process at location 2 that didn't append 10, but appended 20 to the file. Okay? Now I have two different copies of the file. One containing 10, one containing 20. Got it? What I do at location 1 is I read this file and say, it contains 10. Let me append 10. Let me append 15 to that file. So what I do is I append 15 to that file, and it will lead not to what I expected, 10:15, but to 20:15. Okay? Now, write follow read semantic says, listen, I don't mind that I append something, but at least I should be appending something to a file I had seen before. So that means that if you had 10, then somebody appended 20, and then you append 15, you're fine. Got it? Is this clear to everyone? Okay. Now,
why the second version, X2, isn't replicated to L1 replication?
why not?
In the first case.
Why it's not replicated to L1?
Yeah.
Because the distributed system decided that it wasn't necessary to do that. Because all the updates at L2 took place by process at L2 who didn't move location. It was just this stupid process over here that decided to move to L2.
It's not only one process that moves to one location to another. There are multiple processes running.
Yes, there are definitely multiple processes running in the system, and I'm only showing one.
Oh, yeah.
And for good reason, because it's client-centric consistency. It's my view on the world. Okay? Yes?
Why is the read operation?
Let me see why the read operation is relevant. For which case?
Or, if you don't read on location 1, in the above example,
Yes?
then still I think on location
2, the write set would be made, right? So if you then, you don't have to read S1.
No, okay. Your question is, why is the read operation at L1 even relevant?
Yeah.
Because you don't have to do the read, and then when you move to location 2, you simply do the update. Yeah, sure. But that's not the definition of writes follows read semantics.
Yeah, okay, but I don't.
So the read operation is relevant only for the definition.
Okay.
And I'll make this a bit more concrete.
But if you don't read, then it might be different. I mean,
The interesting thing is, if you do not do a read operation, and let me try to make this as explicit as possible. If you do not do a read operation at location 1, the middleware will conclude, hey, this is simple. This guy hasn't done anything. So when it moves to another location, it said, well, you didn't do anything, so I don't have to do anything either. No matter what, if you do a write operation, that's all fine by any of the consistency models I've discussed so far. So the distributed system can lay back and do nothing. You're asking me, what if this is time? What the hell is this write set doing over here? Are you telling me about a miraculous distributed system that can anticipate that there will be a read operation over here, and fearing the worst, it says, listen, every write operation I see over there, I will instantly copy to my location as well. That's what your question is based on.
well, yeah, more or less.
Yeah. Well, such distributed systems exist. They're called pessimistic. I'm dead serious. So again, I'm coming back to make the separation between specification and implementation. I like your remark very good, actually. It's very good. So in this case, I do have a distributed system operating across 2 locations who sees that a file is being updated at location 1, and without even knowing what's going to happen in the future decides, let me pick up this file as well. You never know.
That's the calendar example you gave in the beginning. That's the second calendar example you gave in the beginning.
No, hold it. I'm talking about an implementation. So what this implementation would achieve is also monotonic reads. Okay? Now that's nice. Then I have a single implementation in this case for monotonic reads, and for this example, writes follows reads. So let me now rephrase the question. If I would have a data-centric consistency model, notably sequentially, I would have a sequentially consistent system. Would an implementation of a sequentially consistent system implement any of these client-centric consistency models? Okay, so think about this question. So I have an implementation of a distributed system, and I have a distributed system that implements sequential consistency. Sequential consistency tells me that if I do a write operation, that in essence, if anybody does a read operation, one step back. If I have 2 concurrent write operations, everybody in the entire distributed system will see the same order in which those write operations took place. Okay? So that means if you have read operations, everybody will see things in the same order. If I would do an update, and I would combine this again with causal consistency or whatever, I would still see the same order everywhere. Now, come back to the original question. If you would have a sequentially consistent distributed system, would that system automatically implement every one of these client-centric consistency models? Just think about this. Okay? Yes?
Maybe not everyone, but at least monotonic read.
Well, don't give me the answer now. Just think about this. It might actually be an interesting question for an exam. And actually, I would have to think about this as well. So my bet is yes. Actually, I've never asked this question myself, but my bet is yes, actually. Client-centric consistency is so much weaker than any of the data-centric consistency models, well, not any of them, most of them, and certainly sequential consistency, that I would guess, yes, it would. Your question, indeed, relates to what is this read doing over here? Is it relevant? It's only relevant for the model. Okay, so that's the specification of the model. And I'm explaining the semantics of writes follows reads consistency by means of this example. And your question is, again, what is this write doing over here? And now I'm telling you it's a pessimistic write. What would have been more realistically? So basically, it would have been more realistic if this guy over here could have moved to that point over there. Then you would have a just-in-time implementation of your consistency. Okay? Okay. And by the way, this is again food for thought. If I would move this to that thing over there, what would happen if I would have other write operations over here? Concurrent ones with these. Okay, we're getting into the nasty stuff in just a minute. Now, if you take a look at writes follows reads, it's an interesting example because it automatically implements causal consistency in the case of news. I know most of you probably use Usenet News for downloads. Once upon a time, you actually used Usenet News to read news with all these non-binary groups. And what you could have in certain implementations is that you would read a reaction to a posting before you ever saw the posting. It's a causal consistency thing. And what this thing says is, well, if you read something, that if you want to post an update, it actually pulls in the whole thread before you can actually proceed. And that actually establishes the causal consistency you would want in a normal news system. Okay. Question. If I take a look at these client-centric consistency models, well, the first one important observation. I hope you see that client-centric consistency models can be considerably cheaper to implement than data-centric consistency models. And the big difference is you do not need a global view of the state of the system. To make this practical, if this is my smartphone or whatever, what I can do is I can maintain a token when I log into this system, and when I, let's say, log off or temporarily log off from the system, this token will record exactly where I was. And when I move over to another part of the system, I just hand over this token with all the information saying, listen, I just came from over there, and I did these following things, and then at the moment you log in, this is the just-in-time thing, this guy will say, good, let me copy it over there, and everybody's happy. Now, can you give me an example where client-centric consistency models are going to get you into trouble? Where you will not see consistent information. Let's assume that only clients can modify data. And now I want to have an example where I can still be surprised when I log in over here. No, and everything's working perfectly. No faults. And security is also not. Okay, so I'll repeat this for the recording. If let me see if I got this right. If multiple users are working on the same Google Doc. Yeah, that's a very good example, actually. What will happen in that case? So, and just keep it simple. 2 users are operating on the same Google Doc. And now the system implements only client-centered consistency models. Can you give me a scenario where you will be surprised? Okay, so the same document. Yeah. Okay. And what will you see? So, okay, for the recording, you have 2 people operating on the same document. One adds, modifies paragraph 1, and the other modifies paragraph 2. What will you see? Yes, but that is ordinary concurrency. There's a better example, a much more compelling example. Yes. So here's the calendar, right? My calendar. What you first should realize, I'm operating on my calendar over here, right? And then I move over there, and that's another version of that calendar. It's my calendar. Where's my secretary? She's over here. Is she moving? No, she's not. So that's the reason why it was triggered by your initial opening of a file. She has my calendar, right? And she modifies my calendar, but she's not moving. She's not moving location at all. Comes close to your answer to a certain extent. She's not moving at all. Why would the distributed system even bother of moving that version to wherever I am? It's her copy of my calendar. It's my calendar, but it's her copy. And she's not moving. So she can make all the modifications that she wants. I'm not going to see them. Until the moment that I log into the system at the same location where my secretary is, and then what? So now here's a scenario. My secretary is working over here. She modifies my calendar. I had my calendar over here. I move over there. I modify things, and I move over to that one. What happens? I have a conflict. It's because of synchronization. We call it synchronization in our daily lives, but what will happen from an implementation perspective is that perhaps the calendar that I had over here is moved to that location because that's where I'm now logging in. Oh shit. There's another really other version of that calendar, and I have a major conflict with the calendar that I was working on. And the system is not going to resolve that. If I had a sequentially consistent system, hey, no problem. Because every time my secretary would do an update, would update it, and I would see my calendar being modified. And that's the difference with a data-centric system. I have multiple users, and they will be working on their copy of the data, and you will not notice any conflicts until you have those two users suddenly operate at the same location on the same data. And then you will see, hopefully you will see, well, if there's a conflict, you will then see it. Okay?